All right, so thank you so much for joining for this new reading group session organized by ContinualAI. Today we have the pleasure to host Umar, that you can see here, from KAIST, and who is going to talk about his recent work on, oh, sorry, I don't see the actual title in the slides. So can you share them, Umar?
Yeah, sure. Yeah, so can you see?
Yeah. So we can see that. So thank you so much. So he is going to talk about his recent paper that you can already access on arXiv as a preprint, which is called Towards Continual Online Unsupervised Depth. So I mean, I invited Umar here also because I'm a huge fan on works that deal with depth and looking at these very quickly. I was very interested to learn more about this. I hope that the same goes for you guys. But yes, essentially, Umar will talk more about the intersection of depth prediction and what we can learn from depth using like a continual learning approach. So thank you so much, Umar, for accepting my invitation and being with us today. And please go ahead with your talk.
All right, thank you very much, Vincenzo, for extending your work day into this late hour on Friday, and thank you very much for all the audience for providing me with this opportunity. Let's hope that this is as productive a session as it is. If you have any questions, please don't be shy and ask those questions in the middle of the presentation or whenever you are comfortable. Okay. So let's jump in. The title, as you can see, Towards Continual Online Unsupervised Depth. Okay, so let's start off with the motivation now. What personally motivated me towards this product? Now, AGI, artificial general intelligence, as you can imagine, is a pretty hot term nowadays. Yeah, everyone is talking about artificial general intelligence. And I tried to look into the internet and papers to find a single definition of AGI, but I could not find. Maybe I need to study more or something, but it was very difficult for me to come up with a single definition of artificial general intelligence. But what I found was that there were two types of definitions of artificial general intelligence. First set of definitions is about the strength of the neural network or the capacity of the neural networks. For example, right now we have neural networks doing ImageNet classification with 1,000 classes. Maybe we want it to be as good as human beings, maybe 2,000 classes or 10,000 classes. Or maybe we want object detection with thousands of classes with the accuracy level same as human beings. So this is the strength concept related with AGI, that the artificial general intelligence proposes that neural networks should have the same capacity as human beings. The other set of definitions that I found was about the mode of learning of artificial general intelligence systems, which is they should have minimum supervision. And once they are deployed, they are capable of understanding the scene on their own, and they are capable of making decisions on their own. So basically, another way to put it is that they interact and learn from the environment where they are deployed. Now, one thing very informal that we need to mention here is that for general public, AI is, or AI was actually AGI. The current concept of AI that we have a training session with supervised training, and then we have a separate inference. For general public, this was never the concept of AI. For example, like here, you can see some frames from movies. And in none of these movies, I mean, first of all, if you can recognize these movies, then you have a very bright future in AI. But if you look at what concept we had about artificial intelligence was actually artificial general intelligence. So what is the requirement for an autonomous system to, when it is deployed and it can learn on its own and it is capable of making decisions on its own? So that is where continual learning is a key requirement. Where we have a system, this is deployed on its own, so it is capable of learning new tasks and it is not going to forget past tasks. The other thing is that the data usually that is observed by such systems is temporally correlated. So that means that we have a continuous stream of data coming in, and that requires special techniques for online learning. And then it is not ideal or not practical to provide labels for all the data that is being passed to such systems. So it should be unsupervised or self-supervised. So if we can achieve these three goals with any learning system, basically that takes us very close to the concept of artificial general intelligence, though not in capacity, but in terms of mode of learning. Another way of looking at it is looking at the history of computing, basically, and presume that things happen in cycles. So when computing began, we had centralized computing in the beginning. These days are very rough, so don't take them seriously. Then we had distributed computing. Nowadays, again, we are seeing a resurgence of centralized computing. So if things happen in cycles, what do we expect in the future is we will have distributed computing being the thing in the future. Now, AI and deep learning, they are the major drivers of current cloud computing platforms such as Amazon Web Server or Google Cloud Engine and Microsoft, etc. So what we expect is in the future that the AI is going to be on the edge and we will have distributed systems deploying AI. Now, as you can see, nowadays we have a lot of inference happening on the edge. But if we want to do training on the edge, that's a very different challenge. And if you want to do continual online self-supervised learning on the edge, then it's a huge challenge and it provides us with a lot of opportunities. Also with this comes a lot of ethical issues, because if we have such autonomous systems learning on their own, then the question comes that how much authority are we going to give to machines to make decisions on their own? Now, this authority is easier to control in centralized systems, but if we have a distributed system, then we may have some ethical issues in there. So basically summarizing, nowadays, the more practical approach, pragmatic approach, or pragmatic application of continual learning is that what we want to do is we want to avoid retraining, whereas we have a new task coming in and we have a trained model. So we don't want to go through the whole cycle of training once again, rather than we want to train on the new task only and not forget about what we had in the past. But maybe in the future, in the long term, continual learning is going to play a role in artificial general intelligence on the edge. And that was one of the major motivations for this work. Let's take a step in that particular direction. Also, continual learning helps in the generalization problem. For example, if we have a neural network or a system which is trained, and then it is exposed at test time to a data which it has not seen before, then the results are going to be pretty bad. But if we have a system which is continuously in the learning state, it generalizes well, or it adapts well to the new data. So it can be thought of, continual learning can be thought of a way of solving that particular generalization problem in deployed systems. Okay, now before going any further, there are some hazards or disclaimers I have to make. This particular presentation is more tilted towards engineering. So it's not very theoretically dense. The other thing is, I mean, you can attribute it to my lack of theoretical competence. I'm okay with that. The other thing is, it is about computer vision. The ideas can be extended to other domains, but I don't have personal expertise in, let's say, NLP or text or sound, etc. So that's why here I'll be talking about computer vision. And the other thing, finally, related to the first part, is that I will be more interested in applications, practical data sets, and slightly you will feel that there is slightly less emphasis on theory. There are some very elegant papers about the theory of continual learning, and this may feel slightly different compared to them. Okay, now question, why do we need depth, and why is the focus on depth in this particular paper? So depth is critical to many applications, and I mean, there are a lot of applications where we can use depth, but nowadays in the market, there are two major applications where depth is critical and it has penetrated a lot. One is photography and the other one is navigation. So if you have a smartphone, the self-portrait images that we take, basically, the smartphone is doing what DSLR cameras are doing, but to do that, smartphones need depth of a scene. So what they do is they blur objects which are farther away, and they blur the objects that are closer less, and they create the synthetic depth of field effect, which is seen in this particular image I've taken from a paper from Google. Similarly, the concept of 3D photos that has been used by Facebook for a couple of years, I think, and also Google has also introduced their 3D photos, which is not possible without depth. Also, for navigation, we need to know about obstacles, depth of obstacles, and similarly with autonomous driving, we are interested in depth of pedestrians, depth of cars. I mean, without this information, it's not possible to navigate. So that is why the focus is on depth in this particular presentation. Now, for depth extraction, basically here I have divided them into two methods. There we have passive methods and active methods. Passive methods are generally inspired by human vision or how we perceive a scene. For example, in stereo vision, we have two cameras which are replicating our two eyes. Structure from motion is similar to our sense of depth while we move our head. Depth from defocus is similar to our sense of depth while we look at how much an object is blurred. And then we have monocular methods where we look into, you can say, occlusion, size of an object, this sort of information. So these can be categorized into passive methods. And in active methods, we have an active light source, for example, LiDAR or time of flight. Now, passive methods, as you can imagine, are much more closer to us, closer to nature. But right now, currently, active methods are dominating the market, especially in autonomous driving, because they provide depth resolution much better than the passive methods. However, the problem with active methods is that their spatial resolution is low. Passive methods have higher spatial resolution. Also, there are other issues with active methods, such as power consumption, expensive equipment, and things of this sort. So this is a controversy that has been there for, I think, 2 or 3 years, whether to use passive methods or whether to use active methods. A lot of people use active methods now, but passive methods are still being used in a lot of applications. Okay, now I'll talk about the proposed method. So first, I'll talk about the continual learning scheme and how we do it. And then I'll talk about the depth estimation part. So in this, I'll first talk about the task boundaries, regularization, replay, and the proposed regularization versus replay. And then I'll talk about the depth estimation. So what do we want to achieve? What we want to achieve in here is I want to have a system which can do passive depth estimation under minimum supervision. So we deploy such a system, and it is capable of perceiving a given scene, and it requires minimum, or you can say no supervision in this particular case. So to achieve this, now why we want to do this is because of, as I mentioned, the generalization problem, and as I mentioned that it is much more closer to the AGI concept. To achieve this, what we need is, first of all, unsupervised, because we are not going to provide any labels for any input. Now, self-supervised is a better term, but I'm using unsupervised in here because in the past, authors have used unsupervised with similar depth estimation schemes. The other thing is that the schemes needs to have continual learning in there, so that if we move from one scene to another scene, we don't want to forget about what we had learned about the past scene. And the data is going to be obviously online. It is going to be temporally correlated. So how do we deal with that? And how do we not go to a minima for the current scene rather than we find a solution which is good for all scenes? We don't have any task boundaries. So there is no information available about when a new scene starts. There's no test time oracle. So at test time, we don't know where the task boundaries are. And then we require synchronized operation. This is something I will talk about in a couple of slides. So this is the block diagram, which is, as you can see, quite simple. We have a sampler which chooses from the input samples or the replay samples, and we have a regularizer which controls or which kind of penalizes changes to the neural network parameters. And these are controlled by a distance estimator, which is based on the loss value. So it's pretty straightforward, and I'll go into the details of this algorithm. Okay, now let's talk about the task boundaries. As I mentioned, we are not given any task boundaries in this case. So I'm not the first one to deal with this problem, and there has been a lot of work done for this particular problem. My approach for estimating the task boundaries is very simple. I just get some soft measures of the task boundaries. Basically, what I do is I use the loss values, and I try to estimate the mean and the variance of the loss values using a recursive filter. And then I use the Mahalanobis distance to give a rough estimate of the probability of a new task or a new scene in case of depth estimation. So this particular equation 1, this gives us the squared Mahalanobis distance, and this recursive filter is used to estimate the mean and the variance of the loss values. So if the loss value, if there's a spike in the loss value, we will have a larger Mahalanobis distance, indicating that the scene has changed. This is a very informal way of putting it. Now, as you can imagine, this is a very simple way of defining task boundaries. And these are not hard task boundaries, these are soft task boundaries. And you can imagine they are not supposed to be very accurate. Why? Because number one, at the beginning of every scene, what happens is that the estimates of the mean and the variance of the loss are not very accurate because we are in a kind of a transient state. Secondly, I've not mentioned it here, but if you can see the manuscript, so I've made a normal assumption on the loss, which is a very, very strong assumption. You can say that to say that the loss has a normal distribution. And then again, it's possible that there are some boundary samples which cause a spike in the loss profile, and the system presumes that it's the beginning of a new task, whereas it is the same scene going on. So this is not a very robust method of estimating task boundaries. That is why, first of all, I use soft task boundaries. And secondly, the underlying algorithms are such that they are robust these problems with the task boundaries. So now we talk about regularization. And as you know about regularization, basically the concept is, I mean, most of you are going to be quite familiar with this. We penalize changes to important weights across tasks. For example, two on top of my mind, which are very famous, are the elastic weight consolidation and memory-aware synapses. So they have different measures of importance of parameters, and they penalize changes to important parameters across tasks. This is a very, very informal description of their method. Now, in my case, I have a very simple scheme to define the importance, which is the magnitude of the parameter. Basically, if a parameter has larger magnitude for a given task, then that means that particular parameter is important for that particular task. Now, the intuition for, now, this may seem very simple, but the intuition for this comes from the neural network compression literature, where if there are parameters which are close to zero, they're compressed, they're removed, and if there are high parameters, then they are kept. So basically what that means is those high parameters are important for particular tasks. What we expect is that if a parameter has larger magnitude, it is going to contribute more to the output. This is not as formal as, let's say, memory-aware synapses, where they measure the importance by passing an input sample and computing the gradient, but it works well. So what I do is I add the following regularization penalty. So we have the magnitude. So the larger the magnitude, the larger this regularization loss, and this penalizes the changes into the weights. And I have also included this Mahalanobis distance term d_dt in here. So basically what this means is the penalty is higher if the probability of task or scene change is higher. So this is the regularization term that I am using in this particular work. Now, what happens generally with memory-aware synapses or elastic weight consolidation or similar regularization schemes is that after every task, there is a small delay which is used to compute the new importance of the weights. So there's an aperiodic delay happening at the end of every task. This is not the case in this particular approach, the proposed approach for regularization, because the task importance are updated at every iteration. So by this, the frame rate remains consistent, and that is why I call that the operation is synchronized, and it is important for real-time operation of such systems, so that no frames are lost because of estimating the importance of parameters at the end of every task. Now, okay. Now I've talked about regularization, but now I'll talk about the problems that are there with regularization. And what the summary of it is that tasks are given importance based on how recent they occur. So if a task occurred very far away in the past, it is not considered as important as tasks that have happened recently. I wanted a more formal description of this. I tried to do some Bayesian analysis, but I was not successful. So maybe some of you may be capable of computing this. It's a nice research problem. But here the description is very informal. So let's say we have at time t, the tth task, and the overall loss is basically the loss for the current task and the loss for the previous task, which basically is the regularization term. You can just roughly put it that way. And the loss for the previous task is actually equivalent to the overall loss at task t minus 1, which if we look at is then the task at t minus 1 and then the previous task at t minus 1. And if we go in this direction, we can say that roughly the contribution of nth past task is equal to gamma power n. Gamma is usually less than 1. So you can see that if the task is very far in the past, and then its contribution to the current loss is very low. Much more elegant analysis can be found in the reference 5. The paper Continual Learning requires perfect memory and is NP-hard based on set theory, where they have reached a similar conclusion that regularization does not perform as well as replay, but this is a different way of reaching that particular conclusion. So now we talk about the replay. Replay is quite simple. What I do is I save the input sample if the loss exceeds a certain threshold. So basically what I'm trying to do is I'm trying to save difficult samples for future replay. And why I'm trying to save only difficult samples for future replay is because there are certain psychological models such as spaced repetition which show that systems or neural systems, they easily forget difficult examples compared to easy examples. So that's why I want to maintain information about difficult examples. And once we have these, then we replace input samples by replay samples with equal probability. Not only does it help remember past tasks, and in continual learning, it also helps to break that temporal correlation in the input stream, and that helps against the online learning problem. Now, you may raise this question that why am I basically storing samples? There are much more sophisticated and better way of doing this. For example, we have methods based on generative replay, or recently some methods based on storing compressed features. Now, the reason I cannot use generative replay right now is because to estimate depth or disparity, we need accuracy at a pixel level. And if that accuracy is not available across images, then the whole system is disrupted. We cannot estimate depth. So currently, I could not find generative models which were capable of providing me with, let's say, stereo images, which can maintain that disparity level. So that's why I'm not using generative model in here. For compressed features, well, in this case, the problem is why I'm not using it is generally compressed features are used in classification problems where the label is just a single scalar, whereas in my case, the label is depth, which also needs to be compressed. And the problem is we don't have the ground truth depth available to us. So basically, we can't store the features, and we need to maintain as accurate of the samples as possible. By the way, I have an upper cap on the replay storage of 1.5 gigabits. This is taken from the paper the Remind paper, where they have mentioned this upper cap and some other papers as well. But I hardly reach this cap in my experiments. There's hardly been a case that I've gone even close to this particular storage capacity. Okay, now, I mean, this may be something very straightforward for most of you. Regularization does not require any additional storage for replay, but it requires extra compute. Replay requires additional storage, but maybe it takes more time if we are storing data on the disk. Now, if you are storing it on a GPU or maybe a very fast RAM or SSD, then it is not that slow. But if you are storing it on a disk, then it generally becomes something that takes time. So in my experiments, as I will show it shortly, replay performs better than regularization. However, in this work, whenever I mention proposed methods, so it is both replay and regularization used together. So I have not done that somewhere regularization performs well and I show results only for regularization and somewhere replay performs well. No, that's not the case. Always the results that are shown are both a combination of replay and regularization in this particular work. Now we'll talk about depth estimation, and it's because of the, if you have any questions, you can ask me questions about depth estimation. Here, I'll just give you a very brief summary of self-supervised depth estimation. So first, I'll talk about self-supervised stereo depth, and then I'll talk about self-supervised structure from motion. So self-supervised, it requires basically two cameras, and disparity between the two images, you can say that it's inverse of the depth, and the network learns the disparity indirectly. So we have this left image from the left camera, right image from the right camera. It goes through the left image, goes through a disparity generator network, gives us some disparity. And using this disparity and the left image, we can reconstruct the right image. And the reconstruction loss between the right image and the original right image is something that we want to minimize. And when we minimize that, that helps to estimate the disparity. And in this way, this particular disparity generator network is capable of generating depth of a scene. Similar approach is used for structure from motion. We have a reference frame and target frame. So a target frame can be the next frame, frame can be the previous frame. And we have neural networks to estimate the disparity or depth, and we have a neural network to estimate the pose between these two frames. And then we warp this reference frame using the pose and the disparity to the target. And again, we try to minimize the reconstruction loss between the reconstructed target frame and the original target frame, and that helps us in generating good depth. So this is a very, very brief summary of how we can use self-supervision for depth estimation using stereo and structure from motion. Now I will move towards the results. And results was personally a very, very difficult for me to gather results because we don't have specific data sets for this particular problem in terms of depth estimation. So what I had to do was I had to choose the data sets that are used for depth estimation and use combinations of those particular data sets to validate the performance of the proposed method. So I'm using three data sets in my work: the Kitty data set, which is an outdoor data set, Virtual Kitty, which is a synthetic data set, and the rectified NYU, which is an indoor data set. You will see examples of these data sets shortly. So what I call each of them is a separate distribution. And there's some terminology that you will see in the coming slides. So what I mean by cross-distribution results is that training is done on one data set and evaluation is done on the other data set. For example, I say that the outdoor images are from the outdoor distribution and the indoor images are from the indoor distribution. So what we do is, if I talk about cross-distribution results, this means that I'm basically talking about cross-data set results. Cross-domain results mean results from different scenes. So here I define domain to be a scene. For example, in case of the Kitty dataset, city images are a different scene, campus images are a different scene, road images are a different scene. Similarly, for NYU, you can say the bedroom images are a different scene, kitchen images are a different scene, and so on. So these are different scenes, and cross-domain results will indicate that. And online adaptation results are the results on the current scene where training is being performed or online training is being performed. I've not mentioned all the hyperparameters, but I've used the same set of hyperparameters across all data sets and across all experiments, and the details of the hyperparameters are given in the manuscript. So the first set of experiments is for structure from motion with the Kitty and the NYU data set. And what I do is something called as warming up. So basically, I pre-train the neural network with half of Kitty and NYU dataset, and then online train on the other halves. So this is the pre-training Kitty and NYU, and the method. So FT means fine-tuning, and this is the proposed method. If we online train on the Kitty dataset, the absolute relative error, which should be as low as possible, is improved by using the proposed method. for current distribution, across the distribution, for online adaptation, and for all the cross-domain results. And similarly, the same is the case with the NYU dataset. If we perform online training on the NYU datasets, then the results on the NYU datasets are better compared to fine-tuning. The results for the Kitty dataset are better. The results on the current scenes are better, and across domains, the results are better. To make more sense out of these results, I've included the qualitative results in here. So this top row is the Kitty image, and the bottom row is a scene from the NYU dataset. So when we fine-tune over Kitty, you can see that the results on Kitty are quite reasonable, but the results on NYU are real bad. I mean, they're pretty useless. And when we fine-tune over NYU, so the results on NYU are not great, but the results on Kitty are much worse than that. However, if we use the proposed method of regularization and replay, and we are training over the Kitty dataset, the neural network remembers about the NYU dataset, and it is producing good results with the NYU dataset. And the proposed, if we do the same thing over the NYU dataset, so the results on both the Kitty and the NYU datasets are reasonable. In the second set of experiments, I have done with stereo. And for stereo, I've used Kitty and the virtual Kitty datasets because both of these datasets provide us with stereo images. And so again, pre-trained with half of Kitty and virtual Kitty, warming up basically, and online trained with the other halves. And again, we see that the absolute relative results with the proposed method are much better than if we perform simple fine-tuning. So again, here are the experimental results. If the top row is the Kitty images, the bottom row is the synthetic virtual Kitty images. If we fine-tune over Kitty, results on the virtual Kitty become really poor. If you fine-tune over virtual Kitty, the results on Kitty are not that degraded. However, if you use the proposed method, then the results on both the datasets, regardless of whether we are training over the Kitty dataset or the virtual Kitty dataset, they remain reasonably well. The third set of experiments is based on some recent literature. Here, what I have done is I have pre-trained the neural network on the Kitty dataset and then trained over the virtual Kitty dataset for one epoch, and then evaluate over the Kitty dataset to see how much of the Kitty dataset the neural network remembers. And here we have the comparison with other methods available as well. So L2A and LPF, these are methods which are based on, you can say, regularization-based schemes. And you can see that for all these metrics, the proposed methods perform the best, except for the RMSE metric, where LPF is better. However, if we look at the percentage improvement introduced by our method, so the percentage improvement by our method in RMSE is much more significant compared to the percentage improvement introduced by the LPF method, which means that our method is capable of recovering more information compared to the LPF method. Also, these asterisk mean that in these particular experiments, the L2 and LPF, they have, when they're training on the virtual Kitty dataset, they have excluded the fog and the rain images, which are quite challenging. So I have conducted experiments without the fog and the rain images and with the fog and the rain images. And again, our method shows decent performance. So now the effect of regularization and replay. So you can see that either the combination of regularization or replay, which is shown here as the proposed method, performs the best, or replay performs the best. So never is the case that regularization outperforms replay. And this is what I've seen in these particular experiments. Now I'll just quickly talk about where from here, basically. So I feel that this is just a step towards autonomous learning, and we need more similar steps towards autonomous learning on the edge. Also, this particular work is for depth extraction, which is a downstream self-supervised task. And perhaps we can perform these experiments on other downstream self-supervised tasks, such as anomaly detection, optical flow extraction, maybe something that I'm missing right now. Anomaly detection means that we deploy, let's say, a surveillance camera somewhere, and the system on its own is capable of identifying when something wrong has happened and can trigger an alarm without any supervision of any form. And similarly, optical flow is a downstream self-supervised task. So maybe we can perform experiments on these downstream self-supervised tasks as well. This has a lot of, as you can see, deployment issues if you want to do autonomous learning on the edge. So we need to take into area, speed, power constraints with the hardware. And again, the ethical concerns like how much decision making are we willing to allow to machines, basically. This is something of philosophical discussion. So this is about me, and this is the end of my presentation. So if you have any questions or suggestions, I'd love to hear from you. Thank you very much.
Thank you so much, Umar, for a very interesting presentation, and I really appreciated also the initial, let's say, grounding of the proposal within like a more, let's say, general vision of artificial general intelligence, and then a system that can learn continually using that. I mean, if I can start by breaking the ice, what do you think about the importance of depth towards a more, let's say, unsupervised and autonomous way of achieving continual learning? Because as you may know, and everyone knows here, I think you know, in the last few years we have been focusing on supervised continual learning mostly, I would say, in terms of community effort. And I mean, this is, for example, one of the few works that is starting to address continual learning within an unsupervised, let's say, scenario. And so I was wondering, what do you think about moving towards supervised learning, and also especially, let's say, the importance of depth based on your experience and your vision?
Okay, all right. So as I mentioned in the presentation, I mentioned few of the problems or the practical constraints that I'm targeting. Like, for example, continual learning, online learning, unsupervised, it should be unsupervised, there are no task boundaries, things of that sort. If any of those building blocks is not there, or if any of these constraints is not met, then we cannot do independent or autonomous self-learning systems. So, for example, if we it's a very good vision. It's a very beautiful vision and a very complicated vision to think of systems which are capable of learning on their own. Now, if we focus on, let's say, self-supervised problems or unsupervised problems, that makes it even more attractive, because we are then talking about systems which require no supervision at all. And that is very close to the essence of artificial general intelligence. And there are challenges in that. I don't deny that. I mean, self-supervised generally does not perform as well as supervised methods. But maybe with more data, with clever schemes, we can achieve results which are comparable to the the supervised schemes, or maybe in competition with supervised schemes. But the great advantage that comes with self-supervised schemes is that you don't need any supervision, so a system can work independently on its own. Talking about depth, so I'll be honest to you, the reason I started work on this was because, as you know, in the beginning, or even now more recently, there have been some accidents that have been happening with self-driving cars. So a couple of accidents happened. And what that led me to think was that, and depth is a very critical part of self-driving systems. I mean, this, if you can imagine, it's critical to make decisions about where an obstacle is, where a person is. And probably those accidents, now I don't have the exact details of those accidents, but maybe one of the reasons for those accidents to happen was that those systems were exposed to situations or to test data which they had not observed at train time. So what I wanted was that we have systems which are robust enough to learn depth of a scene, depth of obstacles, let's say depth of cars or pedestrians, while they are deployed. So depth is critical from that perspective. And if we have systems which are capable to generalize to unseen situations, then maybe that can help in avoiding such accidents in the future.
Yep, absolutely. And no, I say this also because, and I mean, there are a couple of papers that show that just depth prediction can be like a good surrogate of a supervised signal to achieve also like general classification and learning, let's say, good features that you can reuse for other tasks. So yeah, I was wondering if you had thought about this and maybe you want to extend this work towards that end. I mean, you use depth and, for example, this approach to have a system that is like learning invariant representations that you can reuse for more, let's say, specific tasks like image classification or something like that.
Okay. So what my aim with this work is currently is to target downstream self-supervised tasks. Like there are self-supervised schemes which are used for pre-training or getting good features, and there's a lot of decent work done in that particular direction. Of course, this work can be extended in there as well. We can learn more features continually and use those features for other downstream tasks. In this particular work, the focus is, or the scope is limited to downstream self-supervised tasks. But if we plan to use it for pre-training, I cannot think of a reason why it cannot be used. So probably this is something I can explore in the future as well. So it's a very good idea, I think. I will definitely take it into account and see what we can achieve with this.
Yeah. So do we have any more questions from the audience to Umar? Please raise your hands or just open your mic and say your question.
Hi, Umar. So I have a question. So can you mention with regard to depth, what example do you think of a downstream task?
So depth extraction on its own is a downstream task, or anomaly detection on its own is a downstream task, or optical flow extraction on its own is a downstream task. Generally, self-supervised methods, they are used as a pretext, or they are used to extract good features for other tasks.
That I understand from classification aspect and how the downstream task work over there. That I understand. But over here, you are doing the self-supervised based learning of the depth.
Yes.
Right. So that is why my question was coming.
So in this case, the aim is to achieve good depth, and we do that using self-supervised learning. So we don't use self-supervised learning as a pre-training. Here we use self-supervised learning to achieve the ultimate goal of getting good depth. So that's why I say that in this case, self-supervised learning in itself is assisting the downstream task, which is depth extraction.
One follow-up on this. So the block diagram you had for the self-supervised learning-based depth generation or depth estimation, over there you have a disparity generator network. So is it like your whole system is being trained through that? Is the disparity generator is also being trained?
Yeah, so that is the neural network basically that is being trained. That includes all the parameters and everything. Yeah.
Okay, thank you.
Yeah.
Okay, any more questions? All right, so I thank you, Umar, so much for your talk again and for your availability. It was a great talk. And so for all the people that are here, please refer to the archive, the preprint Umar already posted there for more details. And I asked Umar to just send me his slides if he can, so that I can upload them on our forum. And I remind you all that we are now working with the ContinualAI to essentially provide a collaborative code base for continual learning, which is called Avalanche. And I already invited Umar to contribute as well with his own algorithms to it. And yes, that said, we will have next week at the same time, another reading group session. This is going to be with Timothy Lesort, talking about his recent work understanding continual learning settings with data distributions drift analysis. So if you're interested in understanding how continual learning can be related to the dataset and concept drift, let's say, well, that's going to be like an interesting session. So thank you again for joining. Thank you all, and see you next week.
Oh, thank you.
Bye.
Bye.